Swayam Prabha. Digital India. Educated India.
I welcome you to this course, to this lecture module of flow through porous media. We have been discussing about interception of fine particles in the porous medium. So, interception of suspended solids. So, in this regard, what we talked about earlier was that there exists something called a zeta potential that whenever a solid surface is brought in contact with an electrolyte, a zeta potential develops. So, this zeta potential this zeta potential can be measured. This zeta potential develops zeta potential develops at the surface, and there would be an electric double layer which develops very near the wall. Generally for a macro scale flow process, for example, flow in a tube, larger tube of millimeter size and all, this electric double layer is insignificant. The impact of this electric double layer is insignificant, but when it comes to a porous medium which can be conceptualized as capillaries of dimensions 1 micrometer or less, this electric double layer can have immense importance. This electric double layer can as we have shown that first of all, if we apply a voltage in a capillary of micron size dimension, 1 micrometer size dimension, if I apply a voltage gradient over the length, that means if I have a voltage across the length of the porous medium, we see that there is a flow possible. That flow is referred as electroosmotic flow, and we have already showed that what would be the electroosmotic velocity, because it depends on the electric field, it depends on zeta potential, it depends on obviously inversely related to the viscosity of the fluid. So, it is basically an interplay of the pull, Coulombic pull on the charges because of the presence of electric field, and simultaneously there is a viscous one layer has to slide against the other. So, that effect. So, the combination of these, so one can get to electroosmotic flow in a micron size capillary, or for that matter in a porous medium. So, electroosmotic pumping, we have talked about electroosmotic pump, where these glass beads are used to create a porous medium, where by application of a voltage a very controlled flow rate can be achieved. The reverse of it is streaming potential. We said that if we do not apply voltage, rather if we apply a pressure gradient. So, if I impose a pressure driven flow, in that case, because of these electric double layer formation, because of these charges accumulating near the wall, etc., one develops something called a streaming potential, which can be measured, a potential drop across the porous medium, and we have talked about that as well. So, with this background, now we would like to see what happens if we look at a porous medium. Here we are talking about crushed barrier sandstone in 0.1 molar calcium chloride solution, and what they did is they measured the zeta potential in millivolt. They measured the zeta potential as a function of pH. That means they took a beaker, put some crushed barrier sandstone, that means the reservoir rock. Barrier sandstone is basically a reservoir rock taken and crushed, and then that is suspended in 0.1 molar calcium chloride solution. So, in this case Z will be 2, capital Z, that valency, that will be 2 in this case, because it is calcium chloride, not sodium chloride. So, in that solution they did these, they stirred it and created a suspension, and then they continue to change pH by adding an acid, or by adding an acid to decrease the pH, or adding an alkali. So, they have changed the pH of this medium, and then they measured the zeta potential. What they found is that zeta potential changes with pH as is given by this red line. So, because of this change in zeta potential, and not only this is the change in zeta potential, one can define in this regard the surface charge per unit weight, surface charge per unit weight of crushed barrier sandstone. So, surface charge means if we talk about a surface and the surface charge it develops, so that is also going to change with pH. Okay, so surface charge is given as coulomb per gram in sigma. So, the sigma is the now this is not interfacial tension, this is the surface charge per unit weight. So, that sigma is going to change with pH as is shown by the red curve. So, what that means is as pH is changed, the amount of charge that would be accumulating on this wall would change. So, that means so the dynamics here. So, this is basically the cation anion exchange capacity of the surface. So, that is highly dependent on the pH of the system. So, what we can draw out of it is when ionic strength of the permeating solution is decreased, when ionic strength of permeating solution, that means we are having a pore and in that pore the fluid is flowing, and then now earlier there was a resident brine in place inside porous medium and it has certain ionic strength. Now we are injecting something whose ionic strength has decreased. Okay. So, the EDL formed at the pore surface and around the fine particle in that case will expand. So, if there is a fine particle sitting on the pore on the pore wall, I mean basically porous medium is comprising of grains, large grain and small grain. Now, a small grain against a large grain, so it was sitting there and they are held by they are held by an attractive London van der Waals interaction. So, these grain and this wall, they are held together by an attractive force which is here London van der Waals interaction force, which is applicable over a distance as large as 10 nanometer. That is quite a large distance over which this attraction is applicable, and this attraction is applicable between two similar bodies, fine particle and pore surface in this case. Okay. So, there is an attraction and because of which they are held together inside the porous medium. Now, when this ionic strength of the permeating solution, that means the solution that is flowing, the ionic strength is decreased, the EDL formed at the pore surface. So, there would be EDL formed and this EDL would take this would be the EDL here of certain charge, and then there would be another EDL developing around this fine particle as well. And then these EDLs will overlap. So, around a fine particle expand and overlap. So, these two EDLs will overlap. So, essentially overlap of like charge surface gives rise to repulsive energy of interaction. So, in this if there would be a repulsive energy because these are the like charges, if these are all positive then these are also positive. So, there would be a repulsion, and that repulsive force will go act against the attractive London van der Waals interaction force between two similar bodies. So, when this force exceeds the attraction force, naturally this particle would be dislodged. So, and this whole process happened because of this electric double layer formation, and because why electric double layer formed is because the ionic strength of permeating solution is decreased. And what is the measure of it? The zeta potential. And as you can see, zeta potential means the zeta potential develops, or zeta potential tells you what kind of potential was developed at the wall because of these because of this permeating solution and the wall combination. So, we can see that this zeta potential changes drastically. It became from 30 millivolt to minus 30 millivolt as the pH is changed. So, if this is the change, this is how it happens. So, then automatically if the ionic strength changes, you can expect the thickness of this electric double layer will also change significantly. Okay. Similarly, surface charge per unit weight, that also changes drastically with pH. So, that is the reason why there would be always a possibility that when you inject something inside a porous medium, so when you inject something, there is this particle may get dislodged from the wall. So, this is one such reason cited for migration of fines. Now, let us see, once the fine is traveling through a porous medium, what kind of conceptual understanding we have. We can think of these porous medium as parallel capillary pathways, bundle of parallel capillary pathways, and we can say that some pathways are plugging and some pathways are non-plugging. Here you can see an example of what is plugging and what is non-plugging. You can see here, this is these, here we see one grains here, and see this red pathway, here it is mostly clear. You can see that this is going to be a non-plugging pathway, definition of which is smoother and larger cross section. Whereas, when it comes to flow through this particular area, there is a possibility that there will be plugging, because there is all fine particles, they are going there, and one can create a situation like this, as we pointed out. So, some particles will enter there and then they will get accumulated at the pore throat. So, if they get accumulated there, this pore throat gets constricted. So, this is going to be, there would be a plugging, that is what we are talking about, plugging here. So, these plugging pathways are highly tortuous pathways with significantly varying cross section. So, that is called plugging pathways and this is called non-plugging. Now, there could be all these phenomena happening. One is called surface deposition. So, generally there would be some deposition on the surface here and there. Pore filling, the pore may be completely filled with the particles, and pore throat plugging, that is pore throat gets plugged. So, that is changing the permeability, but not porosity. Generally, this is the most important concern. Pore filling, I mean, you have to fill, you have to put in lot of particles, and taking all those particles inside the porous medium itself will not be easy. So, generally the porosity does not change much, only problem is this pore throat, wherever there are small constrictions. So, that part, some particles will go and get lodged here. So, that will go and plug the pathway. So, this porosity, which is these parts, that remains clear, but some pathways gets blocked, and so permeability changes. So, now if we look at these permeability reduction, people said that okay, there are two types of permeability reduction possible, one for plugging pathway, another for non-plugging pathway. Plugging pathways, and due to particle accumulation, the change in permeability would be very rapid. So, there would be rapid permeability reduction for plugging pathways. On the other hand, there would be much more gradual permeability reduction in non-plugging pathways. So, you can look at this expression and you can see that here it is e to the power minus alpha f sub e to the power n1. Okay. Now, these are constants. Okay. So, these are basically some constants, and these constants can be obtained experimentally, but this is the plugging pathways which drops exponentially. That means, to start with there was a permeability Kp0 and that declines exponentially, and to how fast it will decline, it depends on f sub p. F sub p is bulk volume fraction of deposited particle in plugging pathways. Bulk volume fraction of deposited particle in plugging pathways, that means plugging pathways. So, now suppose this is the porous block, this is the void volume through which the flow was taking place. Now, let us say out of this part is the plugging pathway, this part is the non-plugging pathway. Now, out of this plugging pathway, let us say this is the plugging pathway, here f sub p is the volume fraction of deposited particles. So, if this is the plugging pathway, now there is a deposition of volume here. So, now this volume of plugging pathways, so volume of solid, volume of deposited particle divided by volume of plugging pathways, that gives me the f sub p, And similarly, for the non-plugging pathways, same volume fraction, bulk volume fraction. So, there is some particles getting deposited. So, this volume divided by the volume of the non-plugging pathways. So, that gives me epsa NP, epsa P and epsa NP, non-plugging and plugging fractions, volume fractions. And on the other hand, these phi PO and phi NPO, these are phi PO is the initial pore volume fraction of plugging pathways, and phi NPO is the initial pore volume fraction of the non-plugging pathways. That means, total pore volume, out of that there is a red line. So, this part divided by the total is the plugging pathways, and this part, the lower part, divided by the total void, that is the initial pore volume fraction of the plugging initial pore volume fractions of the plugging pathways and initial pore volume fractions of the non-plugging pathways. So, basically this, I mean, I am talking, I think I just correct my last statement. Phi PO, that is the this part is the plugging pathway. So, this plugging pathway divided by the total volume, that is phi PO, and non-plugging pathway, this part divided by the total volume, that gives me phi NP. So, that the total porosity can be written as, initial porosity is phi PO plus phi NPO. Okay. And then these N1 and N2 are empirical constants. So, you can see here this permeability at any time would be the initial permeability e to the power, and then here it is epsa P. So, what is the bulk volume fraction of deposited particle? So, it will decline exponentially, whereas here it is declining much slowly. So, these are the permeability here. It is in terms of non-plugging epsa NP, the bulk volume fraction of deposited particle in non-plugging pathways. So, this is how the permeabilities will change depending on what are the how these fractions are changing. I may note here that this is the porosity of plugging pathways. This was the initial porosity minus there is a fraction which is already gone. Okay. So, at any time phi plugging and phi non-plugging, that is equal to the total phi. Okay. And phi plugging at any time is initial phi minus there is this epsa P, it has to be subtracted. But in that case, I must say that this is epsa P is bulk volume fraction of deposited particle in plugging pathways. So, bulk volume fraction of deposited particle in plugging pathways, in that case if phi is the porosity, phi is initial pore volume fractions of the plugging pathways. So, then this epsa P must be against the total volume. Epsa P is the volume fraction of deposited particle. So, that means volume of deposited particle divided by total volume of the system. Okay. And epsa NP is the volume of deposited particle in non-plugging pathways divided by total volume of the system, because if that is so, then only one can write porosity at any time, the plugging part is initial porosity minus this part. So, one can do this exercise provided these epsa P and epsa NP, they are defined as the volume fraction of particle deposited divided by total volume of the system. So, this is how phi NP is equal to phi NPO minus epsa NP. So, this is something which you can do for plugging and for non-plugging. So, now one can define something called Fp, the fraction here, as phi p divided by total phi, and Fnp as phi NP divided by total phi. So, these F, so then the sum of these, obviously since this sum is phi, then sum of these fractions Fp and Fnp, that has to be equal to 1. So, now I can think of split of cross sectional area between plugging and non plugging pathways implies parallel pathways. So, that same drawing that I have drawn earlier, that this is the differential volume of the reservoir that we had, porous system we are talking about, and this is the void in this, so through which the flow is taking place, out of which a part is plugging and the other part is non plugging. So, now we have to treat this as if I am having a parallel flow through these, one is flow through plugging pathway, another for non plugging. So, one can do, if somebody wants to find out what is the net permeability of the system, then one has to consider weighted average permeability, which is Fp into Kp plus Fnp into Knp. Fp and Fnp, these are these two fractions. Evolution of F sub p and F sub Np with time. So, that is one thing which is F sub p is volume of particles deposited per unit volume of total system, per volume of total system. So, and F sub Np is the particle deposited in non plugging pathways divided by total volume. So, in that case F sub p and F sub Np, these are going to change with time, and so there has to be some kind of particle deposition kinetics to define del F sub p del t and del F sub Np del t. So, if one knows del F sub p del t and del F sub Np del t, so with that information now they can find out that after so much of time of if I have a continuous flow and after so much of time, this would be the F sub p and this would be the F sub Np, and based on that information now they can go back and find out what is the permeability in these expressions, because the others are constants which are available, which are determined separately. So, one can put this F sub p, and then so with time how the plugging pathway permeability and non plugging pathway permeability, how they are changing, one can find out, because these are directly relating to F sub p and F sub Np, and one can find out the what is the net permeability of the system. So, how the total permeability or weighted average permeability, how that is changing with time as the flow continuously is going through this porous medium. So, it is critical that this del F sub p del t and del F sub Np del t, that one must have a clear understanding. Now, there are various models available, and there are various suggestions made by researchers that okay, this term should be considered, tortuosity should be considered here, and basically it is particle deposition kinetics. So, there are studies that are already being done now, and based on that one can find out what is the average permeability, and based on that one can find out what is the pressure drop, because that is what finally we are bothered with, that there is a flow taking place and with the flow fluid there is some suspended solid. So, because of this what would be the pressure drop? Okay. So, this is one way of looking at it. If somebody can tell me what is the particle deposition kinetics into two extreme cases, one is the plugging pathway and non plugging pathway, based on that one can find out what is the permeability, and based on that one can find out what is the pressure drop, that is the end point. But I must point out that there is another good amount of work which is done on treating this porous medium as uniform, not as plugging and non plugging, rather focusing on the continuity and focusing on the following the continuity for a particle and fluid separately, and then just follow the standard continuity equations. So, in fact, that is I mean here del F sub p del t and del F sub Np del t, there could be some, I mean there is some amount of hypothesis, some amount of theories we need to deal with, but we will show that when we look at this the other treatment, there it would be somewhat more tangible, I must say. So, in this regard what we do is we are going to talk about continuity equation that means the mass conservation equation. The mass conservation equation is, we are going to do a mass conservation for particle and mass conservation for fluid separately, and you can recall this equation. It is, what did we have for mass conservation? That is, think of mass continuity. What did we have for mass continuity? We had del x of rho u plus del y of rho v plus del z of rho w, that is equal to minus del rho del t, right. That was the continuity equation. So, now what we would do in this case, we will convert this type of continuity equation. Now, we have to write similar equation for solid phase and for the fluid phase, and on top of that there would be some amount of particle which is coming from the fluid phase and getting deposited to the solid phase, which is given by this mu s dot term. Mu s dot is mass of particle withdrawn from the streaming flow due to clogging per unit volume of porous medium per unit time. So, this additional term will be there in the continuity. So, these two terms are basically, you can see, if this goes to the left hand side, so then it would be del rho del t plus del x of this quantity. So, here also we have del t of, now we have a porosity term here, and here we have this into u p rho p, this is equal to. So, this term is basically, we can write these as delta u rho, we could have written, I mean u is probably v rho. So, these three terms is basically this term, and del rho del t, when it goes to the left hand side, it will be plus, only thing is we have additional porosity term here coming, and we have additional term which was not there in the mass continuity, which is this additional term. So, we were going to write this form of equation, and then we are writing another separate equation for the fluid, but this is only for the particle, because this is for the rho particle. So, what we would do is, we will build on this further. So, what we will build on this further in the next lecture. I would expect when you attend the next lecture, just review once again the mass continuity equation that we did in the beginning of the course. What are those terms here? You just go through them once again, then it will be easier to relate what we are going to do now. So, this is all I have as far as this lecture is concerned. In the next lecture, we will build on this continuity equation and take this forward. That is all I have for this lecture. Thank you very much.